Welcome again to my GIS lab. One of everyday analysis carried out by consultants or government agencies is to determine land areas that have a particular set of conditions. Here we will work through an example so that you learn the typical workflow of a geoprocessing analysis. You may be surprised how many steps are involved. We must first start with a question and formulate the objectives and deliverables. In our example, we will ask, within my study area, I need to find all areas where cropland is within 200 meters of streams. The real bylaw states that no spraying of pesticides or herbicides or liquid fertilizer is allowed within a buffer area of 60 meters from a stream. But in this example, we use 200 meters simply to see the results better. We want to make a map to show where those croplands are, and we need to sum up the affected areas. Now that we have our objectives, we need to collect the data, which I have already done. All layers are already in the correct projection, but there's still quite a bit of pre-processing we need to do before we can carry out the spatial analysis. We start by overlaying all the layers. So I have my study area polygon, I have a river file, a line file, and all else I need is my land cover file. And here I have two raster files, two tiles that match together at the edge, hopefully anyway. Before we go any further, we just want to do a quick little test here. So we zoom into an area of interest and simply check out to what extent the river file here. So for instance, this is a river as a raster file from a land cover file, and here's my line file. They seem to fit reasonably well, not perfectly all the time. We need to look at that and potentially make corrections. The other thing we can check out is to what extent the land cover represents true agriculture areas, and we can turn on the world imagery. And now, by having made already this layer transparent, we can also then just turn it on and off, and we can see that the shape of the agriculture areas, when you look here at the boundaries, are quite well represented with our raster file. Now we have established trust that the layers overlay properly and that we can carry out our spatial analysis. Let's look a bit closer at our two raster files. We right-click and go to the attribute table, and we see here the raster value. There are just codes in there, and the count of the number of grid cells, and the same thing we will find for the other raster file, same kind of codes inside. So when we look at the assignment of colors here right now, this is randomly assigned, and I have already found some metadata to explain to me what the individual land cover code would mean. And I have already also added this in my Symbology by simply going into my label and then editing my label and adding the correct information inside here. Now what I would like to do is I would like to not repeat this laborious work here. I want to save this legend as a layer file and then apply the layer file to the other raster file, so they both use identical legends. You can do that by first creating the layer file. You do that by right-clicking, you go to sharing and save as a layer file. So the layer file contains your symbology. I have here the same name as my name in here, and so therefore it just adds here the LYRX and it puts it right into my working directory. And now the layers file was created. We don't see it, nothing has changed, but let's apply this. So now I right click here on my layer that I want to apply it to. I go to my Symbology, and then over here, some people call this icon the hamburger icon. I click there, and there is my import button, so I can import Symbology. And now I have to find my correct folder. And here in my folder, there is the file we just created a moment ago, and you select it and you apply it. And now you can see that the legends for both raster files are identical. Looking also at the display, we have a hard time finding where the original edges were, other than turning one layer off and one layer on again. And around here is our edge, and we cannot see it. So that means these two raster files luckily share the same land cover codes, and they are working together. There was no spatial shift, and we have just gained trust that we can work with these layers further. Now we convert our rasters to features. And we find that tool very easily under our tools, under dual processing toolboxes, in here under conversion tools, under from raster. Here is our raster to polygon tool. And we of course use the correct input file, in this case 825S. It already finds the value field in there. We can give it an output file name. And here's an important part that you must understand about this tool. The Simplify Polygons option is turned on by default. Let me show you what happens if you keep that default on. I hit run, and I already have generated my raster, my output raster file here, and we can now look at the result of simplifying the polygons. When we now compare this with our original raster detail, we losing detail, we creating shapes that aren't there. So I cannot recommend for your raster to polygon conversion when you really want to care about the accuracy, for instance, of land cover files, to use the simplified polygons option. I always turn this off. And now let's look at the result of that, and this looks something like this. So it's identical in spatial extent. It doesn't matter how much we zoom in here, it is exactly the same spatial extent. Therefore, we're going to now apply this for both raster files, and then all we have to do is merge them together into one. We will merge these two polygon files into one by finding the merge command. We find it under the data management toolbox. Data management. Inside the general, there are other ones such as sorting, copying, appending also. We want to apply the merge. We choose our two input data sets. There's one polygon. Here's the other polygon. We give it an output file name, and we hit run. And I have already created my merge output file, which, as we can see, is identical to the other one. I've also already applied my symbology and copied it over. So it's the same symbology, and so this file is the same as these two files were earlier. Now we see that many polygons are still split by the original edge line, and that is kind of a dirty thing to map later on, and we want to clean this data set up. So there is a wonderful command that allows us to do that. and that is called the dissolve command. We find that in the toolbox. And the dissolve command can look into neighboring polygons, and if they share one specific field, then the polygon's shared boundary will be dissolved and it becomes one polygon. Input features is now our polygon here that we have the merged one. We give it an output file name. I already have created one here. And the dissolve field should be our grid code. Grid code is always the field that results from raster to polygon conversion. So the value inside a raster layer becomes a grid code in a polygon layer. That's a default name by ArcGIS Pro. And here we have some very interesting options. Create multi-part features. I will get back to that in a moment. Let's right now have this on, and you hit run. Now when I turn this layer on, you can see the effect of the dissolve command. So what does multi-part mean? We have only a total of 9 polygons because we only have 9 different grid code values. And each polygon is a multi-part in that it consists of tens or hundreds or even thousands of individual polygons. I can go to any polygon and all cropland, in this case, everything with a grid code of 1 has been selected because it's just one multi-part polygon. Let's contrast this when we turn the create multi-part features off and we save it now as a different file and we hit run. Now here I have one that would be called a single part. The single part looks the same. However, if you look at the attribute table, it consists of over 8,000 individual polygons. And now, of course, we can go in and select just one individual, or this polygon here, or this polygon over there. For today's question, it doesn't matter which option you use for the dissolve because the results will be identical. And also I want to make sure that I'm unselecting anything that was selected so that I don't make mistakes later on. Now the only thing we need to do is clip our land cover and our river files to our study area. We do that, of course, with a clip command. You use the clip feature, so the clip feature, of course, in this case is our study area, our input feature, if it was our rivers, and then we would call it rivers clip. So I've already done this for both layers, and here you see the result. I have here my clipped land cover, and I have here my clipped river file. So now we are ready for further analysis. And the first thing we need to do is we need to buffer our rivers by our distance. In our example here, 200 meters. In reality, it would be 60 meters. And for that, we use the buffer tool. The buffer tool is one of these tools that are right on top under analysis tools, under proximity tools, and there's our buffer tool. Input feature would be our clipped rivers. We can give it a name. I personally like to add a name that includes my buffer distance, just so I know exactly which buffer I'm using in case I'm using different distances. You would then, of course, have to set your distance unit to meters. In our example, you would put in 200 meters. And here are some interesting options, and I want to show you some of these. The question is, are you only buffering one side or both sides? So right now we're buffering both sides, and you can also do the left and the right side. The left and the right side of a line means that we have to know the direction of that line. So each line segment here that we see has a direction, and we can visualize this direction by changing our symbology. Within my gallery, I can now search for either arrow, or you could also search for direction. And what I want to choose here is I just want to add an arrow at the end of each line. And there are my default options. And maybe I want to make it just a little bit larger. And if I zoom in here, it becomes clear that all the river segments are flowing downhill. And so now that we know the direction of our rivers, now it would allow us to distinguish between the left side and the right side. I undo my symbology. Now we know the directions of our rivers. Let's look at the various options that the buffer tool has. And let's start off with using all the default options. And if I hit run, then the buffers that we are creating will look like this. So here is our full 200 meter buffers without dissolve. And what that means is that each line segment, whatever line segment we have here, each has its own buffer polygon. And we can also check that by looking at the attribute table. We have 260 individual river segments, and if we look at the buffers here, we also will see that we have 260 buffer polygons. And so in most cases you don't want this. So let's try, instead of saying no dissolve, we want to say dissolve all output features into a single feature. And I've done this already, and the result looks like this. Now we only have one single polygon, right now without an ID. And this buffer covers our entire study area. It's one buffer polygon. That is a great thing to have. Just to show you the differences in our sides, so you can also buffer only on the left or the right side. And I have one example here using the left side, and you see now the yellow buffers are all the ones that are on the left side of our rivers based on the direction of the river lines. And then further and lastly, we have, in addition to our regular buffer tool, we also have a multiple ring buffer tool. And it works exactly the same way, except here you can add, if you wanted to, multiple distances by simply adding the enter key and keying in whatever values you would like. If you do several of these, you hit run. Here is one example of multiple buffers. So here in this case, they all have the same color, but you see the idea: 100 meter, 200 meter, 300, 400, and 500 meter buffer lines. That could be very useful for more complex buffer analysis. But we work right now only with our 200 meter buffer. So that leaves us with just a few further steps. In order to find our cropland within the buffer areas, we have several options to proceed. The one would be that we simply use these buffer polygons to clip out our land cover, and mission accomplished. Another way is to do a spatial overlay analysis. And the best one here that would work is the intersect overlay analysis, which computes the geometric intersections of our, in this case, two input files, land cover and river buffer. Our input features, 200-meter buffer, and our land cover. These are our two input features. They don't get ranks. I have a new output file called Intersect. All the information from the land cover now has basically been added into the land cover. So it's the same thing as a clip. And now we can do our statistics to calculate the area of those areas inside the buffers. We would not have been able to do that beforehand because only now we have calculated new polygons by clipping them out or by intersecting them with another layer. And now we have to recalculate our areas inside here and determine the total area of cropland within 200 meters of rivers. If this intersect layer was created inside a geodatabase, then we already would have our areas calculated and they would have the term shape area. In this case, we can quickly recalculate to make sure that everything is proper, calculate geometry, and our areas have been confirmed. And now the last thing we have to do is we have to calculate the statistics, basically per grid code, the area here, and we can do that by using the summarize command. And my input table, and I have an output table, and the field to summarize is my area in square kilometer, and I want the sum. And my case field, that is the field grid code in this case. So with this syntax, I'm saying for each grid code that is the same, all the ones together, take the field area and create the sum and put this into a new output table. So if I hit run, then I create this output table here. And there, for each grid code, we have the sum of all the area. So in our case, land cover 1 is cropland. So here we have basically almost 10 square kilometers of area that is within 200 meters of our rivers within our study area. And if we select only all those that are grid count 1 from within our intersected file, we can now save it as a new file and simply create one that is only our actual cropland within 200 meters. There is a meaningful map together with our statistic value. Mission accomplished. When you zoom into the river, you can see the quality of your river lines. We see here that they all must be edited because they're not representative of the true location of the river. you have to move vertices. And at this scale, I would suggest that you digitize polygons so that you have a left and a right bank represented in your database. This may altogether take hours or even days to digitize. But you must start with the best data set you can get or create, because otherwise you know that you cannot trust your own results. That's all for now. I'll see you next time.